Hi all, Rob Simpson here again with a couple of questions and observations about the monsoon and a post-monsoon event that just happened around September 9th. By this date, the core monsoon had all but disappeared throughout much of the entire Gulf. I was able to capture sufficient video evidence of the change of wind direction that typically means the end of the monsoon season. But that's a great topic for an entirely other video. As a note, the commentary draws heavily from this paper and the differential between a Arizona monsoon and a New Mexico monsoon. These are themes that are present throughout this video and are dependent on sea surface temperatures throughout the Gulf, but particularly in the northern Gulf, and the highly productive work conducted by Dorothea Ivanova and others regarding inversion layers and CAPE, convective available potential energy, and convective inhibition index, defined in the same paper as CIN, and we'll just call that SIN for the duration of this video and loosely define it as the propensity of hot, dry air to retard the northern propagation of warm, moist air. Under most moisture plumes that enter the northern Gulf of California, a particular rain pattern exists, meaning that there is rain to the west and then rain to the east. When convection and precipitation occurs up here, it draws more moisture in from the south and reinforces the monsoon cycle. Although it did occur in the 2020 season, very little precipitation relative to other locations fell in the low-lying deserts of southwestern Arizona. On August 19th, a lot of precipitation occurred to the east of this oval where very little occurred. It should be noted that some convection and precipitation did occur to the west of Laguna Salada, and this helped to draw much of this moisture plume further to the west. So much of the precipitation that occurs up in this area would not occur without the existence of the western moisture pathway. On 8:30, the rain pattern shifted far to the west. Now, it had already existed far earlier in the season, but this type of rain pattern produces far more precipitation in and above Lake Mead. On 9/11, precipitation contributions from Gulf moisture were east of this line and circled about the traditional monsoon high around the Four Corners region. A highly probable explanation for this moisture path is the existence of approximately a 4,500 foot mesa/mountain range running along the northern half of the Baja Peninsula. During 90% of the days of the monsoon season, a persistent onshore flow occurs from the southwest to the northeast. During the 2020 season, a persistent, consistent cloud cap formed over this mountain range and often induced convection. This would draw in more moisture from the northern Gulf of California. It is my assertion that we need to ask the question of what flooding Laguna Salada will do to this moisture cap and ensuing convection. Here, the brown triangle on the right is the Cucapa Mountains, and this will also have an impact. Energy map for the region showing much of the ridgeline above Laguna Salada and extending all the way down really to the archipelago has reds, blues, purples. This is the location of Laguna Salada shown in blue. One question I have is, can an inversion layer actually form over this location with strong winds and turbulence? I believe that this is one reason why Laguna Salada has such a large evaporation rate. Here is what the forming cap looks like on an otherwise clear day on 9/3. You can see that it propagates from the north to the south in this instance. Looking at it in slower motion and zooming in, Convection can occur along this entire chain. However, in this episode, it's generally from the border down to a volcano directly to the west of San Felipe. It obviously dies down during the afternoon and evening times. Looking at annual evaporation rates, the Salton Sea evaporates about 6 feet per year, Laguna Salada about 8, and this is from actual records when Laguna Salada was flooded to this level in 1987. The evaporation rate above the northern Gulf of California is only 3.3 feet, meaning that there is a large amount of intense, concentrated evaporation occurring over Laguna Salada. In a region where CAP and SIN are predominant, it is only this type of process with the turbulence and low pressure naturally induced by such a process can Laguna Salada experience such an evaporation rate, and this moisture moves to the northeast. Looking at a more traditional monsoonal flow with a core fully intact, this one starts on August 8th, this is August 9th, and you can see the moisture plume moving up to the north. Note that as the moisture plume moves north, it is divided into two sections, a primary eastern section and smaller western section, specifically at the mouth of the Colorado River itself. I believe this to be the result of the propensity of dense dry air to exist over the Colorado River and in some of its subbasins. It is the western section of the monsoonal flow that has to do with the Tres Lagunas project. By the afternoon of the 9th, we can see the splitting of the moisture plumes at the Colorado River Basin and large convective thunderstorms forming on the coastline to the east. Note the dry corridor at the Colorado River Basin. In the 2021 monsoon season, I only saw a few brief momentary bursts of moisture moving off to the north through this corridor. After about 6 years of reading every paper I could find on this subject, most if not all, monsoon models and or theories only focus on the strength of monsoonal moisture plumes and SSTs in the northern Gulf and fail to look at what can happen in the Colorado River Basin itself and how the structure of the basin can focus hot, dry air into the bottom portions of the Colorado River. In this region, the densest air will tend to sink into the lowest areas and will follow essentially the Colorado River Basin and all of its tributaries. Hence, it's this area where the hottest, driest air is focused, meaning the greatest resistance to northward flows of moist air occurs at the mouth of the Colorado. At least in the 2020 monsoon season, this path of moisture transfer seems to experience far less resistance to moisture moving northward and inducing thunderstorms. So in a location on Earth when hot, dry air accumulates and causes a heat dome, moisture flows around it. In our region of the world, and especially in monsoon season, high pressure can dominate the entire continent, but largely focuses on the Four Corners region, meaning that a lot of it drains down to the end of the Colorado River Basin and produces an excess of CIN. So at times like around August 28th, when Hurricane Ida was spinning in the Gulf, causing more moisture to flow this direction, a moisture plume from the south is joined by a moisture plume from the east, causing this type of moisture plume from the northern Gulf of California. As you can see, most of the moisture plume goes to the east or west and does not proceed directly north of the northern Gulf of California. In fact, it is strung out and separated into different moisture flows because of a consistent, persistent flow of hot, dry air down the Colorado River. The convective inhibition index applies mostly to the central moisture corridor of the monsoon and not to the ones on the east and the west, or at least it's most applicable here. To a large extent, it is this onshore flow from the southwest that induces the low pressure zone associated with the monsoon. So, simply speaking, this low in this region that induces more flow north is amplified by evapotranspiration and convection along the Baja California ridgeline. The evidence of this type of moisture draw is reflected in multiple times, even through September. This process is repeated time after time. Within the western moisture conduit, essentially this model does not pertain. An inversion layer is not able to produce itself due to the turbulence caused by the consistent, persistent onshore flow over the top of a 4,500 foot mountain ridge. Here is yet another example of this occurring during this monsoon season. By the afternoon of August 9th, the moisture plume has been split in half and much proceeds along the western corridor. Looking at the water vapor from a different angle shows that the western corridor is highly productive in terms of producing thunderstorms. The massive supercell produced in this time frame in the northeastern corner of Arizona has little to do with Cape and CIN, but more to do with the western corridor. A month later in the season, a body of high pressure develops over southern Arizona. This essentially diverts most of the moisture flow further to the west. And this is a combination of CIN and Cape. The moisture flow is enhanced by the turbulence induced by the mountain ridge along Baja California and diverts more rain further to the west. Generally speaking, the moisture flow induced by moisture plumes from the south can create three different paths of water: an eastern path, a middle path, or Colorado River basin or flow line path, and a western path through Laguna Salada. This is not anything different than what is known about heat domes and how dense air descends. This type of consistent, persistent precipitation pattern that has a core monsoon deflecting off to the east, a Sonoran desert sort of input, and a western input with a gap in the middle that indicates where Colorado River Basin hot, dry air pushes down, is likely more consistent with modern day and future monsoonal precipitation than what occurred even 10 years ago. The propensity for high temperatures and heat domes in southern Arizona is pretty well known and documented. And it is interesting that the hottest and driest places tend to occur east of the Colorado River, directly north of the northern Gulf of California. Looking at some of the history of June, July, August precipitation in Arizona, in '84 we had 7 inches as a statewide average. Is it any accident that Laguna Salada looked like this in 1984? In 1994-95, we had low years, only about 3 inches, and Laguna Salada looked like this. This type of correlation is by no means perfect, and it is dependent on other major factors, especially sea surface temperatures. But in 1999, Laguna Salada did have water in it, not as much as we would like, but probably helped with the monsoon. In short, one of the effects of flooding Laguna Salada should be to reduce the propensity of hot, dry air to penetrate into the Colorado River Basin, but it should also help increase moisture to go from the northern Gulf into this moisture corridor. There are lots of other forcings, and Laguna Salada has lots of other benefits. But one of the benefits may be to increase actual precipitation in the Colorado River Basin during June, July, August. Thank you for your time.